high, that we will have some examples for Pearson's correlation. So the first one is just the paper and pencil example for sample correlation, how to calculate sample correlation. So suppose that we have 1, 2, 3, 4, 5 points, n is equal to 5. And we want to see the sample correlation coefficient. So 123. So maybe it's good to make a scatter plot first. So we have x and y, and x ranges from 1 to 8, maybe. So maybe 8, 1, maybe around 4 here. 2, 3, 5, 6, 7. Okay, so then 120. So we have the 20, 0 to 20. So 120, 120. And 38 is around here. And 610 is around here. And 80 is around here. And 212 is around here. Okay. So overall, that we should have some line with negative slope. So we expect correlation coefficient is probably negative 0.8 or something. So we want to calculate this. Sorry. So xi value is 13682, 13682, and y value the 28, 10, 0, 12. So take summation 20 and 50. And the mean is 4 because we have 5 observations. So 20 divided by 5 and 50 divided by 5 is 4. So this is center. So 410 is the center. Okay, then to calculate the variance, the sample variance, that we need the summation of xi square, also summation of yi square, and the product xi yi for sample covariance. So xi square, that is 1 because, okay, 1, 9, 36, 64, 4, because you can see that 13682. So the square is this. And for y, we get 446 and the 10 square 100, 0 square 0, 12 square 144. And xiyi is 1 times 20, so 20. 3 times 8 is 24, 6 times 10, 60, and so on. Then we can take summation. Then S sub x is equal to the summation of xi square, so that is 114 here, and minus the summation of xi square of summation of xi divided by n, so that is n is 5, and the summation of xi is 20, so 20 square. Then divide by n minus 1, so 5 minus 1, so we get 8 plus 8.5. So sy square, we have the same thing, but for y, then 52. And s sub xy, we have the summation of xi, yi, so this is 128 here. Then summation of xi times summation of yi, then divided by n, and n minus 1, then we get 18. So r square, r hat is the s sub xy, times square root of s sub x, sorry, s square root of s sub x square and the square root of sy square. So that is square root of 8.5 times square root of 52, and then we get 0.856. Yeah, so this is just paper and pencil example for this. And you can use the correlation function. So in R, so COR and vector X and vector Y. So this is the 5-dimensional vector in previous slide, and Y is also 5-dimensional vector. Then you can immediately get correlation coefficient. And of course, you can calculate from scratch. Yeah. And next, sometimes you want to see the correlation is either significantly different from 0. For example, you can see in this figure, maybe this figure, you can see 0.4. So X and Y have some relationship. So linear trend is like this, but it's at least not very clear whether or not X and Y have relationship. So in such a case, if so you want to see if this 0.4 is really meaningful number, or just can happen by chance, even if X and Y do not have relationship. So we want to do the test, and the test, often the Fisher's transformation is used for the test. So this is anyway the approximation. So we don't have the very rigorous theory behind it, but by some approximation, the log of 1 plus r hat over 1 minus r hat. So if the correlation coefficient is 0.5, that means the log of 3. So 1 over 2 times log, this is natural logarithm, log of 3. So this follows this distribution, normal distribution with the center 1/2 times log of 1 plus r naught. R naught is the correlation coefficient for, the true correlation coefficient in the null hypothesis. So usually we set that this is 0. So this is actually the log of 1. So that becomes 0. Then the variance is 1 over n minus 3. So sample size is large. Of course, the correlation coefficient estimate is more reliable. So the n is large, this is smaller, but this is 1 over n minus 3. So using this, you can do the test. So if this test statistic falls in the extreme range, then we reject null hypothesis. Okay. Some center. This is the normal. So this is this distribution. And we can test if r is equal to r naught or not. So think about the rejection region. So we have the area of alpha, if the significance level is alpha. Then the rejection region is here and here. So in this way, that we can test the correlation coefficient. Yeah. So this is the sample code for the condominium price in Detroit. And correlation is actually 0.674. You can see in an earlier slide to see how strong relationship is. Then if we test the correlation between these two, then we get some numbers. And this is actually not the Fisher's transformation, and it uses a different test. But it returns that the p-value is very small, so it rejects the null hypothesis. So this uses a different approximation. Yeah, so you can either use the cor.test function. So this uses the different approximation for correlation, the sample correlation coefficient, or that you can use just the Fisher's transformation. So I will ask this in the quiz or the homework.